Alright, so I had a request for improper integrals. So let's do improper int.m. Alright, so let me pull down, here we go. Alright, so let's integrate, how about 1 over x squared from 1 to infinity, okay? So this is an improper integral from 1 to infinity. I'm going to say that b is 100. In this case, a is 1. And then I need to split my integral into two different loops, right? So my start is going to be 1. And then I'm going to loop while xi is less than or equal to my end, which is b. All right, and then I'm just going to use a standard Riemann sum for this one because I want to make it easy. So Riemann sum is I plus f of xi times dx. And that's it. So what is f of xi? F of xi is the function evaluated at xi. So that is 1 over xi squared. Then I need to choose dx. I'm going to say 0.1. I guess I don't need this a here. And then I need to initialize I need to step my state. So this is integrate. This is step my state. So xi equals xi plus dx. I think this is the first integral. I think we're good to go. First integral. Okay. All right, so then now I need to evaluate the second integral. Okay, now the second integral is complicated because we have to integrate from 0 to 1 over b 1 over t squared times f of 1 over t dt, where, I'm looking at my notes here, t is 1 over x. Okay? So this is where this gets a little bit complicated. So what I'm going to do is I'm actually going to go back up here where it says fxi, and I'm going to replace this with my function xi. Okay, and then I'm going to come up here, make this function improper int. No inputs I guess no inputs, one output. The output will be I. And then down here, I'm going to do function out equals my function in, like this. And then I'm going to copy this back, and I'm going to say out equals in squared. Okay? So now I have this function down here, which is going to evaluate my function here. Okay, so now I need ti to start at 0. And then I need a dt. So I'm going to make dt 0.001. Then I'm going to say while ti is less than or equal to 1 over b. And then I'm going to do the exact same thing I had before. Evaluate the function at ti. All right? So fti is, and remember, it's 1 over ti squared times f of 1 over ti. And it's not f, it's actually my function. Okay? Because what am I doing? I'm taking ti and I'm starting at 0, I'm going to 1 over b, and then I'm evaluating this function. Instead of giving it just t, I'm giving it 1 over t. And then I'm also putting in 1 over ti squared here. All right? I equals I plus f of ti times dt. And then I need to step my state. So ti equals ti plus dt. And then that's it. I'm done. So if I move this over here and I move this over here, and I say, I think it's just, okay, it doesn't like it. An end might be missing, possibly mashing function. Maybe if I put an end here. Ah, Okay, there we go. All right, if I get rid of this end, there you go. I had an extra end down here at the bottom at line 39. Okay, so if I just type in improper int, I get a nan. Oh no. Ah, okay. So here's something that I forgot to mention in class. So when you integrate from 0 to 1 over b, notice that 1 over ti squared is undefined when ti is 0. So actually, I don't start at 0, I start at dt. And now I should be okay. Boom, 1.0507. So now the question is this correct? So I'm going to go compute this by hand and see if I got the right answer. All right, so I just did this answer. I paused it and then restarted it. That's why I have the answer already. So I just did this integral by hand, and I got an answer of 1. So if I hit play, I get 1.0. So sorry, let me clear. If I do improper int, I get 1.05. So I have a little bit of error. If I come over here to dx and I make it 0.01, I get a more accurate estimate. If I do 0.001, I get an even better estimate. I can also reduce my time step on dt, and I get an even better estimate. Yeah, it doesn't look like I get any better on dt. I could make this 100, 1000, sorry. You can just go from there, and you get more and more accurate answer. Note, however, that this answer is only going to be as accurate as the first order method, because we're using a Riemann sum, so I can make b really big, dx really small, and dt really small, and it's really not going to make a difference. I mean, because it's a Riemann sum, I'm still going to get, that's still computing. I might have made b and dx and dt too small. Anyway, there's your screencast for improper integrals. Cool? Good luck.